I'm Steffen Kirchgeorg, and I will be presenting our work on the soft gripper. I'm a PhD student at the Environmental Robotics Lab at ETH Zurich. So I hope my doesn't work. Yes. Forests and their canopies harbor more than 50% of biodiversity, and especially in tropical forests, we can find most of global mammal, amphibian, reptile, and bird species. And these tropical forests cater to the needs of the many organisms. They're so-called microclimates that have different climatic conditions. As we can see on the bottom right image, the forests function as thermal insulators during the day and during the night. They cool the lower canopy during the day, and they warm the lower canopy or the understory during the night. So the animals experience the local microclimate, but not the regional macroclimate. But most of the time, what we measure is the macroclimate. So questions that biologists ask themselves is, what do these microclimates look like? Which species can be found in them? And above all, how will macroclimate warming affect these microclimates and biodiversity within? There's simply too many questions and too little data acquired within forests to give conclusive answers here. This is why we are working on novel robotic data collection methods within forests and their canopies. But how would you go about and collect data in such a remote, difficult to access environment? To date, it is mostly done by labor-intensive work with climbers who can collect data at various heights. There's also forest towers constructed in some places where monitoring equipment can be deployed. And in some places, for example, in Switzerland, we actually have a canopy crane where people can be lowered into the canopy, also sensors be attached to the trees for longer term data collection. But neither of these methods are really cost efficient nor scalable, and sometimes even risky. So we're looking for novel robotic data collection methods. And of course, one thing that comes to mind here is a drone, which can easily reach these distant environments. While drones are ideal candidates to reach those environments, they are quite limited in the flight time, with current drones ranging between 10 to 45 minutes. But if we could exploit the drones not to collect only the data, but to deliver a sensor or maybe to attach to the branches and to the forest canopies themselves, we could monitor longer term data. The challenges we face are quite diverse. Tree stems and branches and their bark are highly irregular, very smooth to very rough surface properties. And of course, they're sometimes very brittle and can break. In addition to that, we experience different diameters and curvatures with all the branches in the forest. So in this work, we are targeting an adhesion mechanism for these surfaces such that a drone can perch and stay within a canopy, or that it can deliver a sensor to the canopy. When gripping natural surfaces, the most common approach is using microspines. So they are basically small needles or hooks. And the microspines usually are brought close to the surface and need to translate along it, as you see in the image, to find an asperity to then latch onto. Usually the failure or also release occurs when there's either overload of the spine or the surface material, or there is slip. And of course, all of these can also happen simultaneously. So an overload and slip of the surface. Therefore, what we want to do is we want to maximize the engagement of these spines with asperities, as well as avoid overload and slip. When looking at state of the art, there's a lot of grippers already existing. Most of them are based on rigid designs where they have a very small range of adjustability, meaning they can only grasp rather flat surfaces. and not very irregular surfaces as we see in the forest. Number two is a palm for rock climbing that uses adjustable microspines, but is limited to this low range of adjustability, which was later then improved with number three. Number 6 here is a very interesting work for UAV perching, where a soft passive grapple was developed, and it inhibits quite interesting properties. So we want to move into the direction on the top right with our target solution. What we have is a gripper that is made out of a palm, a proximal, middle, and distal phalanx, similar to our human hands, and made of soft, deformable fingers. Within the phalanxes, we house microspine clusters. Those clusters have several microspines, and they can, within the clusters, translate slightly by this distance delta LS to adjust at a small scale to the asperities. So what we do first is we align the gripper and bring it close to the obstacle. We then curl the fingers to bring the phalanxes with the microspines in contact with the grasping object. And what we can observe here is that even when being in contact with the surface, that doesn't necessarily mean that our gripper or our microspines are engaged. And we need to actually actively find asperities. So what we do is we contract the fingers such that the microspines find the suitable but also strong asperities along the surface. And here now we can see that contrary to the uncontracted finger, we actually can hook onto the asperities. Once we have achieved that, that means we have also achieved a stable grip, and we can transfer the payload onto the gripper. So how does this translate into a gripper design? We employed, much like other colleagues here, springs as soft elements. And we have these two fingers, as mentioned before, driven through tendons with a differential drive actuation to curl and contract the fingers. And this you can see here in the bottom left video. So we have both bending and contraction of the finger. We then have phalanxes that represent spine clusters with 5 spines each, and each of these spine clusters can translate independent of the other ones. So if we fix one of them due to the differential drive actuation, the other ones can still translate, which is important if we want to attach to as many asperities as possible. This is what we call spine cluster adjustability in the next slides. And then we talk also about adjusting to an individual asperity as much as possible with the multiple spines. And here we have the 5 spines, and we softly integrated the microspines such that they can translate at a small scale. So we have the spine cluster adjustability, where each phalanx can travel independently of the others, and the actuation force is distributed on the phalanxes through a pulley system. For the spine level adjustability, we have a softly integrated spines, and all of them can move independently by delta LS as previously shown. We then characterized these two features. So the spine cluster adjustability, we compared to 2 baselines. One is a fixed phalanx, so we kind of connected all of the phalanxes and actuated it. And one is a distal phalanx where we don't have the differential drive system. What we can see in the graph is that the force, the payload that we can basically hold, we can double or almost triple with our system. And this is mostly due to the independent movement of the phalanxes and the load sharing that allows that basically also avoids slipping and overload of the spines. So the differential drive system is the only one, the only system that maximizes spine engagement and also enables load sharing. On the spine level, we compared the rigidly attached spines with compliantly attached spines. So basically here we have the 2 comparisons. While the maximum holding force does not increase significantly, the mean holding force is maximized. This also makes sense, as by chance all 5 microspines in the rigid design may engage, but the probability of them engaging for the compliantly integrated ones is higher. We did some simple payload test where we tested on different sandpaper roughnesses from K120 to K60, so from low to high roughnesses on diameters of 30, 60, and 100 millimeters. And we can notice that the system works well with rough surfaces at low and high diameters. However, at low surfaces, at low surface roughness, this system can fail, which we see on the bottom right of the table. We noticed 2 failure mode or interesting behaviors. One on the bottom left, even though the gripper was able to hold the payload, we noticed that buckling at low diameters occurred. So kind of the springs and actually the fiberglass backbone that we integrated starts buckling, which is undesired behavior. It can lead possibly to failure later on. And on the right, bottom right, we can see this we considered failure because we couldn't hold the payload, but the gripper was actually able to attach even with such a large diameter. We did some outdoor tests, and you can see that we are also able to attach to inclined branches. We failed to attach on the very right to this tree, as it was both smoother and more vertical than the other 2s. So there we are still struggling with our gripper. We then mounted the gripper on a drone to basically come back to the motivation and show the UAV perching. What you can see is the drone approaching and pressing against the branch and then closing the gripper. Once it fully closed the gripper, we can actually turn off the propellers and perch with the drone there, or we can also think of actually delivering a sensor by detaching the gripper with the sensor. After reversing the mechanism, it detaches and we can actually take off with the drone again. To conclude, I presented a gripping strategy that exploits soft fingers and that maximizes spine engagement with the adjustability on a spine cluster and a spine level. This individual translation of the spine clusters and the spines through the actuation that we chose increases the holding force 2 to 3-fold compared to rigid baselines. Within the future work, of course, it's very interesting to look at properly fully soft fingers made from silicone. This could simplify the mechanical design, possibly reduce actuation force, and allow for integration of microspines across the full finger and thus even engage with more of them. The investigation of finger number and orientation can increase the capabilities of the gripper, especially when looking at more vertical oriented branches or stems. And with this, I conclude my presentation and I'm glad to answer any questions you might have.